So this is a picture of my group this year. It's smaller than usual. And this was the day I'm on sabbatical at the Indian Institute of Science right now. And this was when my group was in my house helping me pack for the sabbatical. So this is all of them right now. It's smaller than usual. Normally it's more like 10, 12 people. I'm a low temperature physicist, so all of the work that happens in my group mostly happens in a dilution fridge. And then some of the projects that are currently ongoing, I heard that some of you are interested in silicon-based quantum dot type stuff, although I don't see the person who I was talking to that about. But so we work on electron-photon coupling and gate-defined quantum dots quite a bit. And the reason for that, the reason for understanding electron-photon coupling is we want to figure out if we can somehow cut off the coupling to make the quantum information in the electrons last at higher and higher temperatures, right? So there is this project. Then my group is also working on defects in silicon clap rates for quantum information science, and this many of you might associate closely with. So as you know, defects in silicon or defects in or defect vacancy pairs in diamond, for example, are used for quantum information science, right? In silicon, one of the problems is that silicon is an indirect bandgap semiconductor, so it doesn't couple well with light. So coupling these defects to each other or to something far away is really hard if you work with diamond silicon. However, silicon has these other forms. So there are these silicon clap rates in which silicon forms these cage-like structures, and you can put a rattler essentially inside the cage, and that rattler, the defect, can act as a qubit. And we are trying to characterize these systems for quantum information science. So the people who do, like carbon capture or materials for batteries, anodes for batteries, they know how to make this. So the chemical engineers and the chemists, they do this a lot, but we just haven't looked at it from the perspective of quantum information science yet. So that is something that my group is working on. And then, like Praveen said a minute ago, I'm working on thermoelectricity in superconducting hybrids. So originally my background was very condensed matter, and I still really enjoy working with superconducting anything. So that's what this project is about. And these materials, so the superconducting ferromagnet hybrids are predicted to have a ZT of about 1.8 at sub-Kelvin temperatures, which would make them a material class of their own. Like there is no other thermoelectric which is efficient at ultra low temperatures, right? So that is what we are trying to figure out there. And then finally, this is a brand new project that my group just started. There are some materials which have chirality-induced spin selectivity. So this would be something like DNA. If you send an electron current down a strand of DNA, it favors one spin over the other, right? So it has chirality-induced spin selectivity. And it turns out that we don't quite know how that works, even though there are some theories, but none of them quite fit. So there is a brand new material which has been discovered at the National Renewable Energy Lab recently, which is semiconducting and has chirality-induced spin selectivity and is not as difficult to work with as DNA, for example. So this project is focused on making measurements on that material to understand this spin selectivity, right? And it's cool because these materials have no ferromagnetism, yet they are spin selective. So in applications where you want spin selectivity, but you don't like magnetism, for example, when you have superconductors in play, then these would be really useful. Okay, so these are all the projects that are currently ongoing in the group, and if some of you are interested in one or more of them, I would be happy to talk about it after the talk. Right now, I'm going to go back and focus on the quantum speed limits with superconducting qubits. So before I begin, everything that I'm going to present today is also in this paper. So if you want to look at specific details of the algorithm or the control sequence or the measurements, you can always look there. So let me talk a little bit about the people who worked on this project. So the samples were made at the NIST Boulder Quantum Electrodynamics Division. So this is Dave Pappas's group. His PhD student Tongyu Zhao, Junling Long, and his postdoc Mustafa Bal. So they made the sample, and they also helped us with the measurements. And then the theory has been done by Jeshwan Gong's group at Mainz. His PhD student Alex and Casey, and undergrads Bora and Kyle, they did all the theory type stuff that I'm going to talk about. And then my group, which is also at Mines, and the measurements were done by my PhD student Joel Howard. This was funded by an NSF grant, and Joel also got a QuizNet fellowship from DOE and NSF. So that's all the funding and all the people. And with that, I'll get started. So before, when I first started thinking about this project, I tried to get back to basics and understand where is the concept of a speed limit coming from, right? So we need to get back and think about what is, like, where does time come from in quantum mechanics? And it turns out that it shows up quite early, right? So this is Heisenberg's uncertainty principle, one of the foundational things in quantum mechanics. And in his very first paper, where Heisenberg gave that relationship in 1927, he also gave another relationship in which time figures, right? So these are two different equations, both of which are statements of Heisenberg's uncertainty principle, right? Now, in the paper itself, Heisenberg never derived these equations. He gave them more as a plausibility type argument. Okay? But this equation, the very next year, was rigorously mathematically derived and widely accepted. But this one caused a lot of trouble, right? And the thing that was proving to be most troublesome for people was this concept of time there, right? Because, like, this equation, when we try to understand it, we say that you cannot measure momentum and position simultaneously, right? And Heisenberg also said it that way, right? So you see that he's saying simultaneously. But then what does simultaneously mean if you have delta t in the equation, right? So this could never quite be interpreted that way. Then it started getting interpreted as a measurement uncertainty, which annoyed a lot of people, including Einstein, right? So Einstein formulated this Gedanken experiment to say that this is not a measurement uncertainty. It's not that if you measure the energy of a system for a time delta t, then the energy shifts by delta E because you've been interacting with it, right? So this experiment was formulated by him just to say that this is not a measurement uncertainty, right? So then the question remained that, okay, if it's not a measurement uncertainty, then what is it? And the first people to kind of come up with a satisfactory theory of it were Mandelstam and Tam. So this is a review paper from 1991, but they did this back in like 1945. So still 20 years after Heisenberg's original paper, right? And they said that this is not a statement of uncertainty. This is actually a speed limit, right? So I'm going from delta t to tau, but they're putting the QSL, the quantum speed limit, in the subscript. And they're saying that if you want to go from one quantum state to another quantum state, there is a speed limit. There's a fastest speed at which you can go, and that is given by this. And they also have a mathematically rigorous derivation of that, right? So still, this was not, even though that puts us closer to what we believe now, it was not completely satisfactory, because there was this delta H, which is uncertainty in the energy, in the denominator, right? So the uncertainty in the energy can be infinite. So your quantum speed limit can be 0. So then other people, so Margolis and Levitin, looked at it in 1996, and they found another tau quantum speed limit. They said the time to go from one orthogonal state to another, which is what this picture from their paper represents. That's the Bloch sphere. You go from one state to another, and that's why they have a perpendicular subscript here. They say that it is given not by h bar over 2 delta h, but it's given by h bar over 2 expectation value of h, right? So then there was some confusion about some additional work about which of these is actually the correct speed limit. And then finally, the same people, so Levitin and Toffoli this time, resolved that in 2009, and they said that the speed limit is the maximum of whichever of these quantities, right? So finally, we have a well-bound speed limit. And just from all these equations and all the mathematics involved, you might think that we are talking about some very esoteric mathematical thing which has nothing to do with real life. And that's why I have all the experimental implications of this speed limit delineated on one side, right? So why is the speed limit important? So first of all, it sets the speed limit for information communication, right? And that is not just the speed of light in this context. It actually depends on the coupling between your qubits. If you try to communicate quantum information between along a chain of qubits, right? It also determines the speed of information processing. It sets a bound on that. It sets a bound on the maximal rate of entropy production, the shortest time scale for quantum optimal control algorithms to converge, best precision in quantum metrology, and spectral form factor. Now, this one is the one that we are most familiar with. So this is the one which says that, there is a, when you measure the spectrum of something, there is a finite line width because there's a finite lifetime, right? So that's where that is coming from. And then for a single qubit case, this has been experimentally demonstrated, right? But for the single qubit case, it is also kind of trivial, right? Because if you look at that relationship that we were looking at, you have a h in the denominator, right? So if I want to demonstrate this for the single qubit case, I can always, what I'm saying is that if you want to make the time to go from one state to another short, then you need to put more energy in. And if you can command infinite energy resources, then you can go from one state to another in zero time, right? So that is a trivial statement. Like if you drive your system harder, you go faster. So that's a single qubit case. If the interesting thing comes into play when you start considering more than a single qubit, right? And you have to consider more than a single qubit, because with a single qubit you can actually do nothing, right? You need at least 2 qubits to do any interesting operations. So then people started thinking about what should we do if you have 2 quantum systems, and this is the famous Lieb-Robinson bound, right? So they considered a chain of spins, and they talked about how information would propagate from one spin to another in this chain of spins, right? And that sets the Lieb-Robinson bound. And then this was back in 1972, and then in 2002, Vidal, Hammerer, and Sirac looked at it as the quantum speed limit for entanglement generation, right? So they said that you have 2 states and 2 quantum systems, and they are in a product state, so they don't care what the other system is doing. If you want to put them in an entangled state, is there a minimum time that it'll take to do that, right? So that is the exact speed limit that they're looking at. And this brings it very much into quantum computing land. It makes it a very real kind of thing. And it turns out that they did come up with an exact speed limit, which we are going to look at in the next slide, right? So that brings me to the motivation for, like, as an experimentalist, why am I working in this speed limit sort of land, right? So first of all, quantum states have finite lifetimes. They have finite coherence times. So because they're not going to live forever, whatever you want to do with them, you have to do it fast, right? And we want to find out what is the fastest you can go, right? But that is the speed limit. So the second very interesting theoretical prediction, which we have not tested yet, but we are interested in testing, is that if you have higher qubit connectivity, then you can actually run faster 2 qubit gates. So those people that I was talking about, Vidal and Hammerer and Sirac, they found the analytical solution for 2 qubits. So they said that if you have 2 qubits and you want to put them in an entangled state, then the speed limit is pi over 4 GZ, right? This is the quantum speed limit time, where GZ is the coupling between the 2 qubits. So if there are 2 transmons, it might be capacitive coupling, right? Then they said that for 3 qubits there is no analytical solution, but numerically this has been shown that if you have 3 qubits, then the speed limit time is still pi over 4 GZ, but then there is this factor in front, and this factor is less than 1. So that means that if you throw a third qubit into the mix, then your 2 qubit time goes down, right? And you can keep doing this. So you can put 4, 5, etc., until finally, if you have n qubits all connected to each other like that, then you can see rate increases of the order of 1 over square root n. So it says that as you build a bigger and bigger quantum computer, as long as it is fully connected, your 2 qubits times will keep going down. So your computer will get faster and faster, right? So that's an interesting thing to look at. And then, sorry, what? Yeah. Yeah. Also, so the operation is still a 2 qubit operation. It's not a 3 qubit. Yeah. One of the Bell states, but also like we'll of 2 qubits. You're going to a 2 qubit state. Yeah. Yeah. So we are comparing apples to apples. So we are comparing the time it takes to send 2 qubits from a product state to a maximally entangled state. In both cases, in one case there is no third qubit. In the second case, there's a third qubit which can talk to either of the qubits, but it is not part of the final state. I don't think so. I think this is I'm not 100% sure, but I think this is a trend, like you do 3, 4, 5 and then say that we are getting this rather than an analytical solution. But I'm not 100% sure on that. Okay, so then again comes the question of, as an experimentalist, what do we do, right? So these limits are all off in theory land, and a lot of approximations are made to get these, right? So first of all, we want to see what is the quantum speed limit in a real quantum system, right? And I'll explain what I mean by real in quotes. So to get this speed limit, for example, you assume that you can run any one single qubit gate infinitely fast, right? And you're not going to be able to do that. Then it also assumes that your 2 qubit coupling you can turn on and off at will. And that's also a non-trivial thing to do, right? So we want to see what happens when you don't have all those assumptions. How close do you actually come to this speed limit? And then it is one thing to say that there is a speed limit, and then it's another thing that if you're given a 2 qubit system, and whatever those 2 qubits might be, they could be 2 transmons, they could be 2 nitrogen vacancy centers in diamond, they could be 2 quantum dots, whatever, right? And I say that, okay, right now they are in a product state, can you put them at the fastest speed possible into an entangled state? You'll have to figure out what gate sequence to run, what laser pulses to put in, what microwave pulses to put in, right? So it's another to figure out what those microwave pulses should be, right? So we want to develop an algorithm to get us that pulse sequence every time. Okay. So the first thing that I'm going to talk about is that algorithm, which will first of all tell us what is the speed limit for a real quantum system, and second, tell us how to get to the speed limit. Okay, so this is an optimal control algorithm, which many of you might be already working with, given what I've talked about since today morning. So I'll still tell you briefly what it does, right? So I have the Hamiltonian of my system, it's H0, and the Hamiltonian of the gate applied is H1. Now, many people at this point get upset with the word gate, so I'll elaborate on that for a second. So in this case, for my qubit system, a gate is just a sequence of microwave pulses. So in the simplest instance, if you have just 1 qubit, right? So let's say your 1 qubit is 1 electron spin, and you have applied a magnetic field, and it's Zeeman split into 2 states. It could be plus 1/2 or minus 1/2, right? And you want to drive from plus 1/2 to minus 1/2, then you have to apply a microwave pulse at that resonant frequency, right? So in this case, your gate is just a microwave pulse at that resonant frequency. So it's something as simple as this. In our case, we are talking about 2 qubits, so it'll be slightly more complicated, but it's still a sequence of microwave pulses. And H0 is just the Hamiltonian that you might have seen before of 2 qubits, Jaynes-Cummings type Hamiltonian, right? The time evolution operator will look like this, e to the power IHT. This is also something that most of you have seen. And we'll break it into m segments. So this is the same time evolution operator broken up into pieces. And then we can say that, I want to get to some state, psi f, and the time evolution operator that the algorithm is working on will get me to state u psi I, right? So what is the overlap between those two states, u psi I and the psi f that I actually want to get to? This is the concept of fidelity in quantum mechanics. So I can say maximize the fidelity. So get me to fidelity 1 to the psi f that I want, right? And then I can just run this algorithm. It'll run like a normal gradient descent, and it'll spit out something like this, right? So this is an example of what you would get if I say that m is 8 and infidelity, which is 1 minus fidelity, is 9.4 e minus 5, and I've given it some initial state and then some final state, and it says that apply this microwave pulse sequence, right? So far so good. So this example is for 2 qubits. Yeah. Or it's a combined gate, like it just gets a full, it doesn't know that this is a 2 qubit Hamiltonian or anything. It just gets a, I see. Yeah. So the two qubits have different frequencies. Yeah. Uh, oh yeah. So for the input variables include my maximum microwave drive strength. So this amplitude is fixed, and then we also tell it the time that we want the pulse sequence to be. So that will be part of. That's a great question because that will help us figure out the speed limit. Because if we give it no time, if we say do this for 0 seconds, then the fidelity it'll not converge to any fidelity above zero, right? So we are not taking decay into account, and I'll tell you why maybe not next slide but 10 slides. Okay. So but no decay. This is an idealized Hamiltonian. H0 is an idealized Hamiltonian. It says that there are two state systems. They are coupled by GZ, and that's all. There's nothing else in the universe. Okay. Yeah. So here what we have done. So a lot of people are using grape in QTIP, the gradient descent QTIP, which is the Python thing for commonly used for optimal control. So this is a comparison of our algorithm with grape and QTIP, right? So this is an interesting graph. So I'll spend some time on it. On the y-axis, I have the time that my algorithm needs to converge to a high fidelity, right? So like I said on the previous slide, if I say that give me a pulse sequence which lasts 0 seconds, then it can never give me high fidelity, right? So I'll start giving it more and more and more time till it finally starts giving me 4 nines or 5 nines in fidelity, right? So that time is TF. T minimum is the analytical minimum, the speed limit, the analytical speed limit, right? So in the correct limits, in the limits in which the analytical speed limit was calculated, TF by Tmin should go to 1, right? If my algorithm is working, it should take me to the analytical speed limit in the appropriate limits, right? Now, what are the appropriate limits? So on the x-axis, I have the drive strength, omega max. How hard can I drive my qubits? And G is the coupling strength. So if you remember, I said that the analytical speed limits assume that you can drive your qubit infinitely hard, that you can run single qubit gates infinitely fast, which corresponds to an infinitely strong drive, right? So, drive protocol, what do you microwave pulses. Omega max is the amplitude of the drive. Yeah. So the analytical speed limit is way over there, right? At maximum drive strength. But you can see in blue is the result from our algorithm. So when the drive strength is very weak, we do not get to the speed limit, which makes sense, right? And grape in QTIP also does not get to the speed limit. That's the orange dots. And then as you start making the drive stronger and stronger, ultimately our algorithm starts converging to the analytical speed limit. But after the drive becomes stronger than a certain limit, QTIP stops converging altogether, right? It just doesn't. So yeah, prefactor, not the frequency. Exactly. Yeah. So actually, we don't know what power it sees. This is the power that we are giving, and we are saying that it is the same power it is seeing because we understand our electron. Yeah. So if there are non-idealities in it, it will show up somewhere. But we have done our best to make sure that there are no non-idealities. Yeah. 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 Enhance that. Yeah. 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 So if we could increase the perceived omega somehow on chip, that would be good. Yeah. The two qubits are interacting short range. This G. Yeah. Yeah. So your H0 can get more and more complicated. Right now, it's only a 2 qubit. Yeah. So in principle, the algorithm is platform agnostic. So you can put in things like that into it. You can put in a different Hamiltonian into it and still run it and see what you get. Okay. So the sanity check that we did this for was to see that the numerical speed limit converges to the analytical speed limit in the appropriate limit. So that the speed limit that our algorithm is giving us is actually related to the speed limit that we are interested in. And then the optimizer can be used for other qubit systems, as I said, right? So till now, we have not given it any information about the particular system that we are using. Okay, so now I will start talking about the particular system that we are using. So our experiments on a 2-qubit system. Okay, so here's just an example picture. I'll talk about it in more detail in a second. And GZ is, for example, these are 2 qubits, 2 transmons, and GZ is the capacitive coupling between them. Yep. So quick primer on superconducting qubits, and I'll go fast because many of you have worked on qubits before. So the chemists and the mathematicians, etc., joke that the only equation physicists know to solve is the harmonic oscillator, the simple pendulum, and that is in fact the case, right? Because when we are given this from phase 1, when we move to phase 2 and we are shown this circuit, we say, hey, this is just like a simple pendulum, right? So this is an LC oscillator, and its energy states look like that. These are the harmonic oscillator energy states. They are evenly spaced, and the even spacing is a big problem for to use it as a qubit, right? Because if you're 0 and 1 and 1 and 2 and 2 and 3 are all evenly spaced, if you put in a microwave pulse between 0 and 1, the same pulse can also take you from 1 to 2, 2 to 3, etc. So your system will, you'll not know where your system is. So we want an anharmonic oscillator. And for that, instead of the inductor, we put in a Josephson junction, which is a non-linear inductor. And then instead of these states, we get, this is the Josephson junction, which is 2 superconductors separated by an insulator. First visualized by Brian Josephson, whose picture is here. And if you do that, then instead of this nice parabolic type potential, you get a potential that looks like this. And your energy states now become unevenly spaced, right? So that's what a transmon qubit looks like. Now, if I drive from 0 to 1, I need a different frequency to go from 1 to 2. So you'll just get Rabi oscillations between 0 and 1 if you start driving at that frequency. The simple pendulum is what? Okay. Yeah. If you do not take it in the small limit. Okay. Yeah. So we are still not. I think the comment is that we are still not beyond the simple pendulum. So if you're done with that course, you can now drop out of the program because that's all you'll ever do. So okay, and this is shown typically in this block sphere notation, in which 0 is the south pole and 1 is the north pole, and any other superposition state is some other place on this sphere. Okay, so this is a picture of the actual chip, and there is a lot of stuff on it, so most of it you can ignore. Here in the red rectangle are the 2 qubits. These are the 2 transmons. And here's a little Josephson junction. Here's a little Josephson junction. These are aluminum, aluminum oxide, aluminum. All the other superconducting parts on the chip are niobium. And these are just the basic characterization of the chip. So this is the relaxation time, and this is the coherence time. And this is the thing why we do not need to worry about non-idealities, because you can see that these are tens of microns, right? And my pulse sequence will be tens of nanoseconds. So for my intents and purposes, the qubit is never going to decohere. So these are 2 capacitively coupled transmon. This is known as a hanger geometry, and because you can see that the qubits are hanging off the main feed line, and I'm going to talk about what that looks like in a second. This is interesting because there's a fixed coupling between my 2 qubits. It's about 7 megahertz, and I can never turn that off. So they're always coupled. So I will never see those nice 0 and 1 state of one qubit, 0 and 1 state of another qubit. This is the spectrum that I perpetually have. This is the spectrum that our algorithm is taking into account, right? So you can see the 2 qubit states are all here, and we have taken into account the 1, 1, 2, 0 and 0, 2 also. Okay. So how are the measurements done? This is that LC circuit that I showed you. This is a classical resonator. And then this is the qubit. And then I put my microwave input here, and then I get an output there. So what happens is that I sweep the frequency of the microwaves that I'm putting in. So this is the amplitude of the readout. This is the frequency of the microwave. And when the microwave is in resonance with the resonator, then I get a big dip. Now this is a dispersive readout. When the qubit changes its state, so if the qubit goes from 0 to 1, the resonance frequency of the resonator shifts. So that's how I can tell what state the qubit is in. And then I can do this many times. And here A and Q, I and Q are amplitudes of two orthogonal pulses, microwave pulses that I'm putting in and the input. And this is kind of what that readout will look like. So you'll get a scatter of points at 0, scatter of points at 1. You can use a classifier to say how many times you found your qubit in 0 and how many times you found it in 1. Excuse me. Okay, so any questions on that, or should I get started on results? That the 99.99 is the fidelity of the algorithm, never of the experiment. So so H0 is giving me those states, and plus I have HI, which is the drive. H1 is the drive. It's strong compared to what? Strong compared to the coupling between the qubits. But the spacing between the states is not coming from like so yeah so I'll start talking about what do we see. So the first speed limit that we find, as somebody astutely pointed out, is go from a product state to a fully entangled state, right? That's how you find out entanglement speed limit. So that's the simplest thing to do, and we do that. And how do we get speed in this context? Like I said before, we keep giving our algorithm increasing amounts of time. So we say take 0 seconds, take 10 nanoseconds, take 20 nanoseconds, and tell me the best infidelity that you are getting, right? So with 0 time, of course, it gets infidelity 1. As you spend more and more time, it gets less and less infidelity until you get infidelity 0 or fidelity 1. And that happens at pi over 4gz, which is the analytical speed limit, right? So we do this. So we do this to get the state speed limit. But state speed limit is also boring in the context of quantum computing, right? Because if you're going to run a quantum computer, you're not just going to go from state A to state B. You want to do something arbitrary, right? Some arbitrary gate sequence. So instead of doing this, we said that the more relevant thing here is to find the gate speed limit. And the gate speed limit is that you say that you start with any state and you end where we don't really know, but you run a C0 gate between these two qubits, right? So just like in classical computers, you can build anything if you have a NAND. In quantum computers, if you have single qubit control and you have a C0, you can build any universal quantum computation, right? So C0 is one of the gates that I'm going to use as an example. But the thing is that I'm going to start with at least a full set of basis states, run a C0, go to the resulting state, measure the fidelity to the resulting states, and this becomes non-trivial very fast. Thankfully, the theorists have looked at it in quite some detail, and they have said that this is what you must do. You must put input Pauli operators, then run your operator, then rotate by output Pauli operators, and then measure the state that you are in. And if you do that, then you'll get fidelity given by this formula. And believe it or not, this paper is titled A Simple Formula. So so this is what we did, right? So this is called process tomography, and this is what we did to find the gate speed limit, right? So these are the two things that I'm going to show you. So for the state speed limit, we calculated an optimized gate from 0, 0 to 0, 0 plus 1, 1 over square root 2. And we measured fidelity of the resulting state to the desired state. And this is what we get. So this is the infidelity to the Bell state. And this is the gate duration, right? Now the green is our algorithm running with infinite power drive. We are saying that you can make that power as much as you like, right? Or just give it some big number compared to your coupling strength. And you will see that you'll get this green curve. And you'll see that it goes to 0 at 1, which is 1 is the analytical speed limit. At the analytical speed limit, it'll give you 0 infidelity. Then so this is just a sanity check, right? The green curve, you can ignore it now. So then we say that we give it the actual drive and we say theoretically calculate the infidelity to the Bell state. And it gives me this blue curve. And then orange is the experiment, and you can see that the orange and the blue curve agree quite well, and they never quite reach the analytical speed limit, but the experimental speed limit does reach the numerical speed limit, right? So this is what we get for state speed limit.
Then we move on to the more general gate speed limit experiment, and we are going to try the C naught first. So for the C naught gate flips qubit 1 if qubit 0 is 1. So if qubit 0 is 0, it'll leave qubit 1 alone. If qubit 0 is 1, it'll flip qubit 1. So it's a very common gate. And so we ran the same experiment. So this is infidelity and this is gate duration. And again, the analytical speed limit is 1 because it is normalized to speed limit. And in this case, green is the intersection of theory and experiment. So that is, if theory and experiment agreed perfectly, the green line would be flat at 0, right? And there's infidelity on the y-axis. And you'll see theory in blue and experiment in orange. And you'll see that it is going much slower than the analytical speed limit. And that is because my drive strength is small. It's only 7.5 megahertz. That big omega is 7.5 megahertz. And my coupling strength, the GZ, is 7 megahertz, right? So it's very weakly driven right now. And one of the things that we wanted to check was that if we drive harder, this should start moving left, right? Otherwise, our experiment is not working. So that's what we did next. We drove it at 12 megahertz. And sure enough, the speed limit went up by 13.2%. So it moved left a little bit, right? And the idea is that if we keep driving harder and harder, we can hit the analytical speed limit. But there are other effects, right? Like it'll heat up your chip. Like you can see that the agreement becomes worse when we drive it faster. So there are reasons why we can't drive faster. Yeah, yeah. Generate heat and also distort waveforms, right? Like we are assuming that the system is seeing the waveforms that we are sending in, but they'll start being okay. So then here is the really interesting thing that we noticed. So we did the same experiment for the swap gate. And again, when we drive at 7.5 megahertz, this is the agreement between experiment and theory. Blue is theory, orange is experiment. But here, there is an interesting thing that you will notice, right? And the interesting thing is that we are actually, the speed limit is at 1. This is normalized to the speed limit. And you will notice that we are actually coming in at faster than the speed limit, right? So this is very interesting to us. And one of the things that we are still trying to figure out, for those of you who have any ideas, I would be happy to hear them out. This is a swap gate. Yeah. This is not the C naught. So this is just swapping the states of the two qubits. So this is running faster than the speed limit. And we think it has to do with this constantly on coupling, right? Because this the analytical speed limit assumes that you can turn the coupling on and off. We can't do that. The coupling is always on, the GZ. And we believe that this has to do with that. Because, it's not just the experiment is coming in faster than the speed limit. The numerical the theory is also coming in faster than the speed limit. So, but we don't know what is happening. But we think that if we figured out exactly what is behind this, then we could use it for entanglement boosting protocols, right? Like if your chip has some natural coupling, then can you design your protocol so that they run faster on that chip? Something like that. That the problem with our chip is that we do not have tunable coupling. So this is our attempt to try to see if the bug can ever be a feature, right? Like there are tunable coupling chips, but ours is not. It has always GZ7. So in our chip, we can't change it. But the experiment you're suggesting is legitimate. We could make a chip with higher coupling and see if this becomes even more pronounced. That's the blue. The blue is the simulation. Faster than the analytical speed limit. Yeah. Yeah. We have not tried, but yeah, that's a good point. We could do it for the blue, like the blue curve we could reproduce at any. Yeah. Yeah. So actually, Jeshwan Gong's group is working on figuring out like what is causing this, and how. Let's say you want to do some particular calculation, and your swap is favored by your chip configuration, but your C naught is not. So then do it mostly using swaps, that sort of thing. So he might have actually tried that, the blue curve, with other things. I've not asked him. Yeah. Experiment, we are using single photon microwave pulses. Yeah. Okay. So then the thing that we wanted to do at this point was to try doing, you remember how we talked about, if you have a fully connected quantum computer, the 2-qubit gates will get even faster, right? So at this point, we wanted to make a 3 or 4-qubit chip, try it. But this was back in like 2019. At that time, it was not easy to us, easy for us to get a chip out of the fab which would have all the couplings that we wanted, right? And it was very important for us to have equal couplings from qubit 1 to qubit 2, qubit 2 to qubit 3, etc., etc. So my PhD student developed a software framework to automate this multi-qubit chip design. At the time, there was no Qiskit metal. And by the time he was done with this and we were ready to publish, IBM announced Qiskit metal. So that's rather unfortunate. But the software is still, the software framework that he designed is still on GitHub. So it's called Qubit Simulation Module. And what it does is that you tell it your device geometry. So you tell it that, I have aluminum here, aluminum oxide here, silicon chip here, etc., etc. And it'll quantize the circuit. It'll spit out the energy levels. And then you can tell it that, I don't like these energy levels. I would like them to move here and here. It'll go back and iterate and give you an alternative layout. So finally, you'll end up with this K layout file, which you can take to the fab, make your chip, and if the stars align, you'll get the energy levels that you want, right? So that's what that does. It's available here if you want to look at it and play with it. Okay, so basically it does the same thing as Qiskit metal, except it doesn't have all the features, of course, but it has a lower, less steep learning curve if you want to look at it. Okay, so now what are we working on? So first of all, this is that 3-qubit chip that we designed using that QSM framework. So we are working on doing this 3-qubit experiment that I talked about to see if the 2-qubit gate actually gets faster if a third qubit just sits there. Then we want to explore higher qubit connectivity. So if we go to even more qubits, how do we get this all-to-all coupling? So there are some other configurations that we are looking at. Then, like I said, Jeshwan Gong's group is developing entanglement boosting protocols leveraging existing coupling. So trying to figure out why is that swap gate running faster and what can we do with it. And then to quantify trade-offs, right? Like, so it's one thing to say that if you put in more and more qubits, then your gates are getting faster and faster. So it makes sense to put as many qubits as you possibly can. But there are also trade-offs to that, right? Like there'll be crosstalk, which you can't get rid of. Your Hamiltonian will become less and less representative of your actual system. And we want to quantify that for NISQ era devices, right? Like, what can we do right now? How many qubits is it optimal to have for the computers that we have right now? Okay, so before I finish, this is a shout out for Mines. So Mines is the top national university in Colorado, according to the US News and World Report ranking. There's that picture without the snow, again, that same mountain. And we have the one of the nation's first MS programs in quantum engineering, which has fellowships available. We have fully funded PhD programs in all STEM disciplines. We also do certifications in quantum engineering for PhD programs. And we're always looking for motivated MS, PhD, and postdoc candidates. And if you want to look for a short-term thing, then this is the Fulbright Fellowship is what I'm on in India right now. So they also do the reverse fellowship where you can go to the United States short-term for various things. More information is available at usief.org.in. So people can, masters, PhD, postdocs, faculty can apply for a Fulbright Fellowship and spend a few months at Mines doing whatever research they find interesting. So there's that. So those are just some ways of collaborating with us. And then I'll summarize the relevance of the things that I just talked about, and I'll stop there. So the first thing that I talked about was that we developed a machine learning inspired algorithm to find the fastest gate to go between 2 qubit states, right? So in any number of qubit chip, how will you go from one 2-qubit state to another 2-qubit state fastest? That is what this algorithm does. And we got some pushback when we were trying to publish this about how people might be reaching the speed limit automatically, right? So the procedure for actually running these algorithms typically involves a lot of manual twiddling, right? So you run what you think should be a C0 gate, and then you end up with a state which is actually not where a C0 would have got you. So the PhD student who's chained to the dilution refrigerator operator stands there and twiddles the microwave powers until he or she gets a good C0 gate, right? So there's this manual twiddling involved. So we got this pushback saying that, that manual twiddling is actually getting you to the speed limit automatically. So we actually went through and checked all of the famous record qubit fidelity type papers, and these are the papers for which you can actually calculate the speed limit. They have given enough information in the paper. They're recent papers. So this is the time that their 2-qubit gate is taking. This is the minimum time that it could take, and this is the time that they're taking divided by the minimum time. So you'll see that actually they're not close to the speed limit. In fact, they could be like 11 times off, right? So the speed limit is not something that you arrive at by chance, but you can do it on purpose by using that algorithm. So these 3 are the numbers from our paper, right? Then the other thing that we did was that we experimentally demonstrated commonly used 2-qubit gates at the fastest speed limit allowed by the interaction strength, of course, and also showed like how it will look for a real system instead of this idealized system that the analytical calculations use. And then finally, we developed this automation protocol for multi-qubit chip design. So with that, I will thank you, and I will take any additional questions that you have. Followed by C0? Why is that in particular interesting?
That's obvious. It's just taking a product state to product state.
Okay.
C0, on the other hand, is maximally entangled.
Mm-hmm.
So that way.
I see. Interesting. Okay, yeah, thank you. We can try that. Yeah. Is the number what? This is the upper bound on how fast you can run this. How slow you can run? That's to follow. Yeah. So you are saying in my case, it's not an electron, it's a photon. Yeah. So you are saying, can you go from 10 to 01? How will the speed limit be broken? Like if you are waiting for the system to relax, then that is way after the speed limit, right? Or you are saying that maybe you are running some complicated calculation for which the speed limit is longer than the relaxation. Then would the relaxation yeah that including decoherence effect somehow, or the bath somehow, an environment increases the speed limit. Yeah. Mm-hmm. I don't know the answer to that. Yeah, but it could be like a theorist could look at that and see. Yeah. Like where the 2-qubit speed limit would not be pi over 4 gz, it would be pi over 4 gz and some function of omega, the big omega, right? Yeah. Thank you all very much.